Very good morning to all of you for these lectures which we have been continuing on sediment transport in rivers. So, continuing of that we will discuss more details how we can quantify how much of sediment transport in a rivers. Looking that I just added very good one of the good publications, okay, which is operational hydrology report 47, which is a manual for the sediment management and the measurements. That what we will be following this chapter exclusively, as well as we discuss about this book and the river mechanics books, that the emphasize what we will do it. Let us understand what is the basic concept when we talk about sediment transport mechanisms, like incipient motions, the bed load, the suspended load, then the flow resistance in alluvial rivers. What are the basic concepts? The concept is started from experimental plumes. The series of the experimental plume as well as the river survey were conducted many part of the world, okay. Basically in Europe and United States of America. So, try to look at with a relationship with the flow and the sediment variables. The most of the often we can measure the discharge, we can measure the velocity, we can measure the flow depth, we can quantify the friction slopes. So, similar way we can compute this, get the sediment concentrations, the bed load rate, we can get the particle size distributions curve. So, those the data, the compile it and analyze it with a new today's concept which is called the data mining concept, which is earlier way back 1950s or the pre and post of the World War II. People have been using that techniques not in under a umbrella of data mining concept, but the same concept, the correlations analysis, visual plot analysis with a different non-dimensional forms. So, today we are talking the same concept with a more probabilistic frameworks, with a more advanced algorithms to mining the data to extract the informations or the relationship between dependent and independent variables, which we are looking at, that if you can measure the flow variabilities and particles, sediment particles or the bed particle, bed material characteristics, can we compute how much of sediment loads are there, or can we compute how much of the bed loads are there. That is what we do it, and that is the reason if you look at, there are the empiricals developed. As I said it, it is a close to the pre and post World War II, the sealed numbers for the incipient motions, which are still extensively used with a new data sets and all, but it is a cross validating that the flow resistance in alluvial rivers, which is a major emphasis, that is what also look at in a two forms in Einstein's equations. I will just focus on 1950s, then INFLIBNET Hence approach in 1972. Then I will talk about the Mayer-Peter bed load formula, which is 1948. So, if you look at that, these are the equations already conducting a series of experiment at the plume levels, collecting data from the field levels, smaller rivers or the bigger rivers, compiling all the data, conducting the data mining concepts to establish the relationships. That is the relationships are the empirical relationship, introducing a new concept like this particles Reynolds numbers, as we discussed in the last class, or the grain Reynolds number. They both are the same, but many books they put particles Reynolds numbers or the grain Reynolds numbers, the sealed numbers, the Einstein's, the parameters. So, many of the new non-dimensional forms of is introduced to establish these empirical relations, even if relative errors. So, the question is that what we are doing, can you obtain a statistical significance between the flow variable and the bed sediment characteristics for a sediment transport process like incipient motion bed load, suspended load, flow resistance. That is the basic questions what today we are going to address. So, this is the basic conceptual framework. So, if this sediment transport, if you look at it, it is a complex and the stochastic natures, but many scientists they try to make it solve these problems using a set of non-dimensional analysis, data analysis, establish the empirical relationship. So, looking that let us come back to the figures what is showing clearly. You can understand it, these bed loads are happening it here. So, bed loads are happening, okay, and there are the bloom of suspended loads are there and some dissolved loads are there, basic mechanism. So, these the process of the bed load from bed materials is going to the bed load, which is a very thin layers along the bed, which will be the dimensions of a thickness that what will be just it will be lesser than of the 3D values. Okay. D is the representative dimensions for the particles, bed material particles. So, that basically if you look at that and there is a very thin layer of bed loads which move along the rivers, and then there is a exchange of the sediment particles from bed to the suspended or suspended to the bed. That is the process happens it. That is the diffusion process what is going to happens it. It is a continuous process. It is a continuum of process what it happens it. So, the wash load which is eroded and washed from upland areas and hardly gets a deposit in the channels. That is what we are not focusing more. Okay. Now, if you look at that, look at microscopically what is actually happens when you have the flow through that the suspended load. The basic concept is the turbulence. If I want to put it, it all depends upon this fluctuating the velocity components which is there in the 3-dimensional and which is responsible for generating the eddies, generating the mass exchange between the layers in different directions. It also generating the shear stresses or equivalent force component because of the fluctuating velocity components. These are the responsible for the eddies formations, the mass fluxes due to also the momentum fluxes, and those are responsible to keep the suspended sediments in the suspension states. That is the turbulence characteristics. The plays a major roles. Those are the studies recently many people are doing it, which is one of this Professor Sobhas's their book, you can refer it, but here in these lectures I am not going to that related, but now the people are relating the turbulence characteristics with the bed loads, with the suspended characteristics and the incident motions. But as this course is meant for the river engineering point of view, so we will be not going to know much details on the turbulence characteristics, but overall it's the sediment is supported by these turbulence eddies and movement in a suspension stage. As the turbulence is decreases, the intensity decreases, then it again start depositing this suspended particles. Now, if you look at bed loads, as I just discussed, is that it can have a rolling, it can have a sliding, it can have a saltations, okay, and there will be particles moving it, and there are the particles goes up, come down like this, okay, and there are the wash load which is doesn't come back. If you track the particles, it just goes through as a suspension level, doesn't participates in the fluvial process of depositions, erosions of the river bed. So, if you look at that, this thickness is 1 to 3 times of the particles diameters. This zone is called bed surface layer. These are the small layers where the bed loads are moves, is a thin layers where the bed loads are moving it. That is the bed surface layers. The laminated loads with the sediment that join the motions from the surface subsurface region under high stress conditions. If you have a very high extreme plot conditions, that is what it happens it. And as says that the sediment motions we cannot separate between the suspended load and bed load separately. Sometimes we combine that, we call the total load, which is the summations of bed load and the suspended load. So, we target about that, we do not separate between that, but some of the empirical equations we have where we can look at what could be the bed load, what could be the suspended load, and there are the empirical equations are there, we can compute the total loads. So, that is the bed load. There is a exchange between bed load to suspended load, bed material to the wash load and suspended load at bed. So, all the process are happening. Sometimes it happens is that this bed materials which is there that can join directly from the bed to the suspended layers. Okay. If you have a, or you can have the bed load to suspended load and suspended load to bed load, that exchange happens. That is the reasons its called is that the sediment motions as a continuum. Continuum we can say that is a because of continuous exchange between these loads. Okay. That is the concept, we can understand it. Now, if you look at that, what type of patterns of sediment transports happen in river? If you look at that at the low velocities, the sediment slides, rolls, moves like just initial stage with a very low velocity and the stream powers is very low. In that case, you can observe any of the plume or the river that the sediments are just starting the bed load motions, just rolling and sliding it. If you further increase the velocity or the stream powers, what will be that? Suspended load will be increases, and that is what is the final. But in case of the river, if you look at when you conducted the experiment, the uniform sand experiment in the plume, that is the characteristics is different, because when you go for real river case, you will have a non-uniform sediments, the sediment of coarser grain and the finer grain. What actually happens in the river case is the finer particles they remains in the suspended case load, and the coarser particles like gravels and all they remain as a bed loads. So, that is what is happens in any ordinary rivers. You can see these finer particles are the suspended load, because you can understand from that, and the coarser particles moves at better. Now, if you look at that, if I plot very interestingly is that tuning of the sediment movements, that is what we are talking about here. It's what is indicated for us is that if you look at that the x axis is the diameters and y axis is the fall velocity, sediment fall velocity, as we discussed in very beginning in the class. Threshold shear velocity, if we plot on that, the sediment fall velocity is the graph of E and F. Okay. So, as the diameter increases, the sediment fall velocity is going to increase it. But if you try to look at what is this threshold shear velocity, beyond that is sediment start the motions. Okay, that means incipient motions. That the conditions it happens it, the line which will cross through the COD, and this line of A and B is representing our particles Reynolds numbers, how it is changing it. So, if you look at that, these two curves, if I try to introduce for you, these two curves are indicate for us different regions. For example, if you look at the COD is the conditions of sediment initiations using a shear velocity as the, that means incipient motions. Okay, more detail we will discuss in the sealed curves. So, the shear velocity is nothing else, is a root mean square of the velocity component, vertical component of fluctuating velocity. So, that means B dash, that the square root mean of that. Okay, it could be the time average components. Okay. So, this is what it indicates. So, what is the shear velocity components, if you want to talk interest more the turbulence things, you can understand it is what is the shear velocity because of fluctuating velocity components, because of the fluctuating velocity component in vertical directions. So, if you look at that curves and the zone of the sediment zones, first I can look at this curve between the area which is covered by DOE. So, that means I am talking about this is the regions DO UV regions. These are the regions. What it actually happens it, if you look at that the fall velocity is greater than vertical component of fluctuations. That is the reasons sediments try to deposit it. Sediment try to deposit it. Okay. So, that is the reasons. These are the reasons what will happen, the sediment will be try to deposit. So, this is the sediment depositions regions, where the fall velocity is higher than the fluctuation velocity component. Region between CO and the OE, CO and the OE, if you look at this part, okay, what it actually happen in these regions, that the fall velocity is a lesser than the vertical component of fluctuating velocity. Because of that, what is actually happens, that sediment particles which is transport from the upstream, they do not settle there, they transport to the other part. That is the reasons sediment transported to downstream directions. Okay. The sediment whatever generated it, that does not settle that is what is transported to the downstream. So, these are the regions where you will have the sediment transport downstream. The sediment remains in a suspension state, no exchange with the bed sediment. Now, if you look at next things what we are discussing, the distance between DO and OF. Okay. So, DO, these are the regions, these are the regions. In these regions, if you look at that, the turbulence is not strong enough for sediment in suspension, the sediment is moved as a bed load. So, this is the part the sediment move as bed load, where's bed load. Okay. Beyond this curve, the above CO and OF, the bed load and suspension loads are coexist, higher the shear velocity that. So, these the regions falls between the suspended load. So, if you look at that, if I just plot the diameters and the fall velocity or threshold shear velocities, which is in centimeter per seconds, clearly it indicates for us that there are the 4 zones it happens it. Suspended load zone, the sediment transport downstream zone, sediment deposition zone and the bed load zones. Here it can have the suspended and the bed load, both combinations can happen it. Now, if you looking that, let us go for the next levels, that to know it at what time the sediment start moving it, that is what is the incipient motions. This the experiment can be done at any plume if you have with a sediment the uniform sands, then you increase the flow or change the slope of channels if you have a tilting plume. So, you can try to know it at what conditions the bed particles which are there, they start moving it. Since the process is stochastic and complex, we do not look at a single particles to move it, because even if you call it a uniform sands, but that still is a gradations are there. And there are the many neighborhood problems are comes it that means not only the particles work like individuals, and still we are talking about non-cohesive materials, bed materials like a sand or the gravels. Okay. So, if you look at try to look at, that is what is the huge experiment conducted within field 1936 to find out the incipient motions for non-cohesive uniform sand. Okay. It is both the things is uniform and non-cohesive state. What he got is very interesting is that is the particles Reynolds numbers or the grains Reynolds numbers has a functions of the sealed numbers, okay, which is and that functions plotting all these are the dots are all experimental data, and they try to look at these functions. Okay, how does these functions varies? Okay, and how we can define it. This is a motions. This is a no motion zone. Okay, this is the motions. This is the no motions of the sediment zones. So, if you plot between these particles Reynolds numbers or the Gaussian numbers and the sealed numbers, which is a ratio between these, the shear stress by the submerged weight of the sediment particles. Those, if you plot it, the functional behaviors like this, it's quite interesting. It's follow a saddles, and as these are experimental data and the process is the complex and stochastics, you will not take a single value, it will get a range of the data range. Okay. We will get the data range because of uncertainty involved in the experiment, uncertainty involved in the data to collect it. Okay. It's and uncertainty itself in the process, which we are not looking that much of details what it happens at the particles levels. So, if you look at that, the dividing this line between the sediment in motions or not in motions, that is the line which is the sealed curves is indicates for us. It says that this it follows very interestingly. If you look at these curves, that when you have the sealed number, the particles Reynolds numbers is equal to 10, that is the point it is here. Okay. Particles numbers is 10, that is the value is that we get the minimum values. Okay. We get the minimum values. Okay. So, that means a critical shear stress divided by the submerged weight, that will be the minimum. Okay. That is the minimum force is necessary to start the motion of the sediment particles. Okay. Particles Reynolds numbers is lesser than 2, where there will be a proportionality. So, these are the linear proportionality zones. Okay. The proportional to the particles Reynolds numbers. When you have a Reynolds numbers, particles Reynolds number more than thousands, these values is comes to closer to a constant values. Okay. So, that is what is that. As you go above beyond hundreds, you can say that more or less it is a constant, and that values is coming out to closer to the 0.045. So, many of the times we try to look at that means incipient motions are independent to the particles Reynolds number. This curve is a similar nature of the curves of pipe flow, where we compute the friction factors. The same curve, the nature of the curves are same as we are changing for hydraulically smooth zone to the rough zones. As you go for the hydraulically rough zones, the shear stress is necessary to bed particle to move it, it becomes independent to the particles Reynolds numbers or the grains Reynolds. Beyond these 10, grain weight and incipient motions are increases. Okay, there are slight bit increasing patterns are there. Please try to have a interest about these sealed curves. As a river engineers or field engineers, we should have a good confidence on the how to draw a sealed diagrams and how we can use these sealed diagrams to know it whether the river is at the mobile conditions or the sediment is at transport conditions or the sediments are not in a transport conditions. That is what we can quantify it, because it does not need much to do it, because all the parameters you can get it from river bed materials. Now, if you look at if I talk about the flow resistance, okay, in alluvial rivers. When you talk about the flow resistance in alluvial rivers, if you know it, the alluvial rivers having different bed forms, as we discussed in the last class, that the ripples, domes, the sand waves and the antidotes. Okay. We need to look at the bed resistance and the bank resistance, because most of the times the river is much wider. So, the bank resistance we neglected it and we focus on the bank bed resistance. Okay. So, the basically what is that you will have a ripples and the dome phase. We are not going much as I discussed in the last class, that how the Manning's roughness coefficients varies as we changes from the bed forms. That is what we discuss more details. So, I am not going more details, and you can see more interestingly, if you look at that, when you talk about this flow resistance equations, that means we are talking about energy dissipations. So, here the bed forms, if you look at when you have a deep with rivers, there are a lot of flow separations and turbulent structures happens it. The similar way when you have chute and fluid, there will be wave breaking process are happening it. You have a boils formations and all. So, those are also responsible because of the bed forms more the energy dissipations. So, that is what will be coming to the flow resistance equations as compared to the plain bed, is compared to the washout domes or the anti-domes with the wave breaking or the anti-dome of the standing wave. So, these the roughness, the domes with the refills, domes, these safe the beds forms are the play the major roles, having a local turbulent structures like formations of eddies, the formations of boils, those creates dissipates the energy. That is the points what I want to highlight it, and that is the we look it in form of energy dissipations. In the form of energy dissipations, we look at that part. Now, if I go for next, there will be grain frictions, this is because of the particle size, okay, and the eddies is created by the grain on the channel bed. Bed form resistance due to existence of the bed forms, and the results are separation of flow at the peak of the sand waves. Rule of the eddies created by bed form resistance, bed load movement is not as direct as the grain frictions, that you try to understand it. Now, if you look at the bed resistance in alluvial rivers, it has a composition of two parts. The shear stress we can divide into two parts. One is the total drag force along the alluvial rivers can be defined it. One, the drag force or the shear stress per unit area, that is what easily grain roughness, form roughness. And that what again we can write it, the shear stress is in form of friction slope and the hydraulic radius. So, we defining this hydraulic radius separately for grain roughness and the form roughness, that is you try to understand it. Okay. And the last class we discussed that we can define the velocity distributions of a channels which will be a logarithmic velocity distributions. Here we are using the log, okay, not natural log, that is the difference is there, is the shear velocity. Here we have introduced that the grain roughness can have a RB dash, the xi is a functions with the function of Ks by delta. Delta is the thickness of laminar sublayers, K is the representing roughness which is generally considered a D65, and this is the shear velocity. So, this is the velocity distributions we consider it as the two dimensional flow which is not affecting, okay, and with a plain bed, that is the conditions what we consider it. Now, if you look at next equations which is very interesting equations by the junior Einsteins, okay, Barbis is 1952. He tried to establish between these two ratios. So, the U2 dash is represent the shear stress, the shear velocity due to the forms, okay, shear velocity due to the forms, and the prism velocity, these ratios will have a functions of Einstein's parameters which defined as the unit of weight of the solids, unit weight of waters D65, and RB1 is the equivalent hydraulic radius considering the bed formed, and Z stands for the friction slope. So, if you look at that, and he tried to find out what could be the relationship functions of f considering the a series of the field data set. That this relationship, the f function that he established from the field data. He just identified two non-dimensional parameters. One is the ratio between the velocity and the shear velocity due to the bed forms. Due to the bed forms, this ratio is a function of a parameter which is defined as a Einstein parameters, the sediment Einstein parameters, which is the functions of the D35, functions of the hydraulic radius for the grain resistance, and you have energy slope. That is the relationship, it is that. And if you try to look at next slides, we can see it. These are the functions what you can see that how xi, the velocity distribution xi is varies between this ratio between ks by deltas. That is what you can see it. Okay. Okay. And this is the hydraulically smooth regions, this is the hydraulically rough regions. Okay. How xi's values vary from 0.6 to the 1.6, and it is become 1 when you have a ks by delta. Okay. Delta stands for the thickness of laminar sublayers, that becomes 1 when it is more or less it is the highest xi factors we consider, and then it becomes to be again come back to the 1 value when you have a hydraulically rough beds. Okay. The same way this Einstein parameters, the functions is behave like this, and these are all field level of theta. These are all field level of theta. That is the reason again a hypothesis that we need to have a data from the rivers. If we do not have the data from the rivers, we cannot conceptually make much more than whatever is existence equations, and each river tells a different story. That is the river characteristics. So, if you look at that, these are the Missouri rivers and different rivers in mostly from United States, and those river data, if you plot it that and try to establish these equations, that is what is there. And here it is there how to if a given water discharge is there and bed materials, can you compute the total hydraulic radius due to grain and form. The basically the same concept that we are using the Einstein equations, and we are trying to velocity distributions equations, we are trying to find out the discharge. So, because these are nonlinear equations, we follow trial and error methods. Okay. Trial and error methods, but today's because we have a lot of mathematical tools. So, I do not think that we should look at this trial and methods how to do it, but as a students you just look at how to do the procedures, because you have a two nonlinear equations. To fit that nonlinear equations, you have to do a hit and trial methods till the discharge and bed material characteristics is satisfied, and that is what we do it. So, there are this is called the trial and error methods, which is the stepwise it is given it how we have to do the trial and error methods. But what I do encourage is, because now a lot of mathematical tools are available, so we can solve these equations using that tools, not the trial and error methods. Same way, if you look at the England Hansen's 1972, he actually introduced the new concept is that the shear stress acting along a lateral can be divided into two parts. Again the same concept. Okay. Will be the drag force due to the grain and the form roughness, and the J here he is putting it this energy losses component or friction slope component can define in two different way. Okay. And he is trying to establish is a theta and theta dash, which is a tau divided by this submerged unit weight of sediment particles. And if you just look it, reframe it and look at that flow intensity due to the grain and flow intensity due to the bed form is theta 1 theta 2 dash, and you can have this equations form. And he also established a empirical relationship with a different bed forms like a dunes form, sand waves, the stationary waves, and all the data D50 values of different data, they plot it, they get the characteristics like this. To follow these ones, he established the relationship between the grain frictions and total bed resistance. So, theta dash is the grain frictions and theta is the total bed resistance. He established the data and approximate the data with a different linear fringes, okay, different linear fringes to solve these ones. That is the reason he has put in different equations. If you look at the for incipient motions, theta that for flat bed, and these theta dash will be equal to theta. That's what it's indicating it your case when you have that stage. So, here also there is a procedure how to have a state discharge relationship, again using that equations, because and this graphical data, that is the reasons again you have to have a heat and trial methods, like first you determine Z and H from the field data, compute the theta from, since you know the theta value, you can compute the theta dash, which is the grain frictions, the resistance relationship between grain frictions, then you can get the H dash, and then you compute the U for the 2-dimensional flow, you can make it hydraulic radius with the different things and determine the channel cross section area corresponding to the end, then compute the discharge. That is what will be stage discharge with different H values, repeating the value. So, you change the H values, compute what could be the Q value as the H and friction slopes are changing it. So, for a different cross sections you will have a different discharge. So, that is the reasons we can develop a rating curve H versus Q, which takes care of the bed form resistance and establish a relationship. So, that is what is theoretically using this bed forms resistance and the grain resistance, we can establish the rating curves, the stage discharge relationship. That is what is mathematically here we are doing it. If you have a H value, you have a energy slope, then you can from the cross section the data and then you get the theta value, theta dash value, H dash, then use that relationship and try to find out that flow area, velocity, compute the discharge, again you compute the different H. That is what is the procedure, and finally you get the points and you can fit a curve. Okay, you can fit a curve to find out what could be the rating curves. So, that is this is another way. If you have a cross section data, if you have the slopes, okay, that is the biggest issue, that energy slope. If you have the energy slope data and the flow depth data accurately, we can establish the discharge using this relationship. It is a quite interesting for us. Now, before leaving these concluding these lectures, I am just introducing the similar way how much of bed load is a transport is you can establish we can have a empirical equations. That is what is by Meyer Fetters, is a long back, it is 1948. Okay. Establish a very complex equations. If you look at that, it is a very complex equations establishes between the part of discharge pertaining to the bed, the coefficients of the bed resistance, roughness coefficients, rate of bed load, these AVs are constants. See, if you look at these equations, is a very complex equations they established way back 1948 to compute the bed loads, and This is the data which is indicating for us that Mayer factor formula with a measured data how accurate it is. Okay. So, that is a comparison formula, and this is the data what is used, the range of the data what is used, a large quantity of experimental data like the plume considering from 0.1 width of the plume is 0.15 meter to 2 meters. Okay. Flow depth 0.01, it is 1 centimeter to 1.2 meters, energy slope from 0.022%, the density is also varying 1.25 to 4g, diameter of sediments also goes to the up to 30 meters. So, it is a huge data, it is a data mining. So, if you try to look at now the present concept, we can talk about it is a data mining, the huge data, wide range of the data, experimental data used from different depth, flow depth, energy slope, and analyzing that they establish these equations. So, next class we will just discuss more about this. With this let me conclude this today lectures talking this quote that we forgot that the water cycles and the life cycles are one. With this let us conclude today's lecture. Thank you.